Everybody is ready? Good. So welcome to our ReNewQuantum seminar. We are very happy to have Gerald Dunne from the University of Connecticut, who will talk us about mining perturbation theory and how to do resurgence-inspired extrapolation, analytic continuation. Please, Gerald.
Thanks, Marcos. Nice to be here. I wish I could be in Denmark, but some other time maybe. I'm going to talk about some work that actually Ovidiu gave a talk about some of this in the last seminar, but I'm going to concentrate more on applications. And also, if I have time, I'll talk about several applications in quantum field theory, just to show you exactly how some of these methods work. Okay, so just to state the problem that I want to talk about. It very often happens in applications that we're facing a difficult problem, and the best we can do is to compute some number of terms in an expansion somewhere in parameter space. But very often we're interested in the behavior of the function near some other point in parameter space. And that other point may be quite distant from the original point. And this is a very, very common situation. And physicists are, of course, very creative, and they think of certain methods to work in certain cases. But I want to ask the more general question: is there something consistent that we can do? So we can term this inverse approximation theory, where you're given some information about a function, and you want to try and rebuild the function as globally and as precisely as possible. So the question is there a best way to mine this limited data to learn something? And we take some inspiration from resurgence. There's, of course, growing evidence, as people in this audience know very well, for resurgent behavior in physical functions. And resurgence suggests that there should be expansions about different points that are quantitatively related generically. So the underlying idea here is to ask whether we can take advantage of this structure, develop new optimal, and in practical cases, near optimal extrapolation and analytic continuation methods. These could be in the physical domain, or if we're dealing with an asymptotic expansion, they would be applied in the Borel plane. And in many applications in physics and in differential equations and integral equations, the Borel plane has some structure. It's not just a random distribution of singularities. And it has structure for a very good reason. It is the non-perturbative physics of the problem, the structure of the singularities. And that non-perturbative physics itself has structure. So the Borel plane is not just some unpredictable random distribution in most applications. So the strategy is going to be to try and nail down this Borel plane singularity as structure as precisely as possible. And if that's possible, then this enables a much more precise analytic continuation back in the physical variable. And the basic toolkit is extremely simple, actually. It's conformal maps, uniformizing maps, and methods within the Pade class, Pade and variations on Pade. And the other thing, inspiration we take for resurgent functions is that for resurgent functions corresponding to certain nonlinear differential equations, for example, or even PDEs, some of the structure that we need is actually known a priori. And Ovidiu talked more about that in his seminar, and I won't talk much about that today. My motivation is really coming from problems in quantum field theory. And resurgence suggests that there are very deep connections between perturbative and non-perturbative features of quantum field theory. So the types of things I'm interested in are, given some information about weak coupling expansion, what can you say about strong coupling? Likewise, given some information about a high temperature expansion, what can you say about the low temperature limit? Or an adiabatic expansion, what can you say about the non-adiabatic situation? Euclidean quantum field theory, to Minkowski, et cetera, et cetera. These are the types of problems I'm interested in. And here's a list of some big unsolved problems. The QCD phase diagram. So when you try to do Monte Carlo methods for quantum field theory, Euclidean quantum field theory at finite density, there's a fundamental problem that the chemical potential retains a complex part to what you would like to interpret as a probability density. This is a very well-known old problem. And there's no generic solution, but part of the solution would be to understand how to analytically continue path integrals. QED, quantum electrodynamics, is very well understood at low intensity, but it's completely not understood at high intensity, either experimentally or theoretically. And it's complete terra incognita. And there are explicit proposals at DAISY in Hamburg and SLAC at Stanford to probe this high-intensity regime, combining electron beams with very high-intensity lasers. And this is actually the problem that introduced me personally to Resurgence at first. Now, what do we know about perturbation theory in difficult quantum field theories? In QED and QCD, we know the renormalization group functions to fifth order in perturbation theory. These are heroic calculations, and that's the limit of what can be done at present. The electron magnetic moment, anomalous magnetic moment called G-2, is known to fifth order in perturbation theory. The fifth order is calculated numerically, partially, and it represents 15,000 five-loop Feynman diagrams. It's an absolute tour de force and has spectacular agreement with experiment. The muon anomalous magnetic moment is one of the big outstanding problems in the moment because there's a discrepancy between the experimental measurement and the theoretical prediction. When we come to other field theories, non-gauge theories, let me list some things about some scalar theories. 5/4 theory in 4 dimensions with, say, an ON symmetry. The anomalous dimensions and beta functions are known now to 7th order. There's been great progress in the last, say, 5 years on this. 11th loop order, there are accurate bounds due to HEP, so-called HEP bounds. And the recent tropical Monte Carlo methods of Oliver Schnetz and Michi Berinsky suggest that numerically 20th order would be accessible if necessary. The phi cube theory in 6 dimensions with various couplings, which has a lot of applications in field theory, but also in condensed matter physics, is currently known to 5th order, exactly in closed form. And in other field theories, for example, a lot is known about integrable and supersymmetric theories. There's been huge progress in the recent years in studying amplitudes and renormalization group properties. But we're still hovering around the 5th order, 10th order type regime. And so I think it's a ripe time to ask, suppose we get into that regime, what can we actually do with that information in order to connect with non-perturbative physics, which is typically calculated with different techniques. So just to set the stage, let's take a very simple problem to start off, get a feel for how accurate things are and what can be done. Let's take the generic behavior of functions in most applications in physics. So here's an asymptotic expansion around x equals plus infinity, and the coefficients grow factorially with some power and there's some overall strength. So the offset of the power tells us something about the fluctuation exponent near this singularity. B here tells us the location of the leading singularity, and this Stokes constant tells us about the strength of the contribution of this singularity. This, of course, is a very explicit problem in mathematics. This is the one that Euler was first studying. It's the incomplete gamma function. This is just the coefficients of the expansion of the incomplete gamma function. I can scale b to 1 very simply just by rescaling x. Now this function has an exact non-perturbative connection formula if we rotate x by this way by pi or this way by pi. There's a difference that is exponentially suppressed. So this is exact non-perturbative connection formula. The Borel representation of this function is also very simple. It's just a simple function with a branch cut if alpha is non-integer. And the expansion just gives you, of this Borel function, just gives you exactly these coefficients here without the n factorial. So now the question in this context for this problem would be, suppose you only had a finite number of terms of this expansion, how accurately could you reconstruct this Borel transform function, and how accurately would that give you the exact non-perturbative connection formula of the function you're looking for? So an interesting feature of this is that one of the really great ways of analytically continuing the Borel transform function beyond its radius of convergence is Pade. We just represent the truncated function, which is a polynomial, as a ratio of polynomials. Now, for this generic type of behavior here, it turns out the Pade polynomials are known. Recall that in Pade, the polynomials in the numerator and denominator satisfy a three-term recursion relation. So you immediately learn that orthogonal polynomials are going to play a big role in studying the asymptotics of Pade in general. So for this function, they're actually Jacobi polynomials. The indices of the Jacobi polynomials reflect the power alpha here, which is related to the offset of the coefficients. And the uniform asymptotics of these Jacobi polynomials is known. It's actually moderately recent. I was surprised to see how recent it is, but the uniform asymptotics is in terms of these Bessel functions. And you can now look not at the expansion around p equals 0, which remember governs the large x behavior, but you can look at the behavior as p goes to infinity, which governs the small x behavior. And from this uniform asymptotics, you see that as p goes to infinity, it scales like this. And if you then transform back again, this tells you that you can go from x equals plus infinity all the way down to some x min, let's call it, and you just choose whether you want 1% accuracy, 0.1% accuracy, whatever. The point is, if you decide on the accuracy you want, the location, the point to which you can extrapolate down precisely within that precision scales like 1 over n squared. So this is amazing. Pade is really trivial to apply, and you already get this very impressive increase in the precision at small x from an expansion about large x as a function of n. So you increase your truncation order, and you can automatically extrapolate down to smaller values of x. I also want to point out this combination here reflects the fact that what Pade does is it actually generates its own conformal map in the limit as n goes to infinity. And we see here the conformal mapping variable that I'll talk about on the next slide. And there's a very deep theory here due to Szego and more recently due to Stahl, which interprets Pade or represents Pade as an electrostatics problem in 2 dimensions, where the poles and zeros are regarded as electrical charges with logarithmic interactions. And what the Pade procedure of representing the function as a ratio of 2 polynomials actually achieves is that it minimizes the electrostatic capacity of that configuration of charges. And that is a very rich theory relating to orthogonal polynomials, but it also gives an interesting physical interpretation of what's going on. But one of the problems with Pade is that even though it gives you a very good extrapolation in this sense from large x down to small x, it's not very accurate near the branch point or near the cut. So it's not very good at accessing the connection formula. Fortunately, there's a very simple cure for this, which is just to make a conformal map. So remember, this problem has one branch point, which I've normalized here to be at -1. So there's a branch cut, say, going from -1 down to -infinity. So we can make a conformal map of that cut plane into the unit disk, which is represented now in the z, by the z variable. And it turns out, again, even in this conformally mapped plane, the Pade polynomials can be derived exactly. And again, the Jacobi polynomials, but the index is different. The index is 2 alpha instead of alpha. And the variable is the conformally mapped variable. In fact, the inverse of the conformally mapped variable. But since they're Jacobi polynomials, we can again look at the uniform asymptotics at large n and anywhere in p. And this tells us now that as p goes to infinity, it actually scales very differently. It scales with n to the 4th. And so this means that the accuracy for some chosen level of accuracy, you can now extrapolate from x equals plus infinity down to some minimal value of x approaching 0. And that scales with 1 over n to the 4th. So again, if you increase by a factor of 10, and you get a factor of 100 improvement over just doing per day. The other advantage here is that this per day conformal is extremely accurate near the branch point and near the cut. And the reason for that is that the Jacobi polynomials, of course, lie in an interval. And here, because of this conformally mapped structure, they actually lie on the next sheet in the original, in the Burrell plane. And that means that they don't interfere. And so let me show you how this works just graphically. So here are plots, I think, of the imaginary part of this function. And here is the exact one. And you see a jump in the imaginary part going from -1 down to -infinity. If you do per day, you see that per day tries to represent this cut by placing a set of poles along what would be the cut. And as n goes to infinity, they accumulate into a branch cut. And the density with which they accumulate tells you what type of, what's the index of or what's the exponent of the branch point. If you actually just did the conformal map, mapped into the conformal disk, but didn't do per day, you would get a slightly better representation, but still have these poles and these unphysical wiggles. But if you do the conformal map and per day, and map back again, you get an extremely accurate representation of the behavior near the branch point and along the branch cut. So for now, this simple exercise, which is actually quite relevant in many examples in physics, that the dominant singularity behaves like this, the message is that very, very simple steps that are really easy to implement can lead to dramatic improvement in extrapolation and analytic continuation, both in how far you can go, in distance, but also in angle in terms of rotation. So let me give you a more detailed example. So this is a particular example of a test case in numerical analysis. It's often used there to quantify extrapolation techniques. It's the Painlevé-1, which shows up again, as we all know, in many applications in physics. It's a simple nonlinear differential equation, and it has this extremely interesting behavior that it has a five-fold symmetry. So there are anti-Stokes lines in the complex X plane. And if we generate what's called the Triton-K solution as an expansion around X equals plus infinity, just as a series in inverse powers of the natural variable, the Écart variable is X to the 5/4, as you can just see by a simple scaling relation in this equation. If you make this expansion of this structure, then it's straightforward to generate these coefficients just by inserting this ansatz into the equation and getting a recursion formula for the C's. But we know from 100-year-old mathematics that the five-fold symmetry of this equation tells us that asymptotically, it looks like a Weierstrass P function in terms of this Écart variable. And so the generic solution to this Painlevé equation is a meromorphic function. But if you tune it like this, so that you just have this expansion in inverse powers of X, you've actually now fixed the two parameters of the boundary conditions. And that tunes it to what's called this Triton-K solution. And there was a conjecture now proven by Ovidiu and collaborators due to Dubrovin that for this Triton-K, the poles of this inherently meromorphic function only lie in this 2π/5 wedge between this anti-Stokes line and this anti-Stokes line. Okay, so that's, just remember in the Weierstrass function, it has a lattice of poles everywhere in the plane, but if you tune the parameters of the Weierstrass function, some of those poles can disappear off to infinity, so you can end up just with hyperbolic behavior or trigonometric behavior if you tune the parameters appropriately. So that's what's happening here, but in a more complicated way in this deformed Weierstrass equation. So within this 2π/5 wedge, the structure of the solution is not anything like this. It has a second order pole at some location, and then an expansion, and then at the quartic term expanding around that pole, there's a second constant that appears, and all the other coefficients in this expansion are just polynomials in x-pole and h-pole. Again, analogous to what happens in the Weierstrass function. So the question here is, suppose you just have a finite number of terms of this expansion developed in this x equals plus infinity regime. That's what you might think the function looks like, that structure. However, if you analytically continue in the complex plane around to here, you go through these Stokes transitions, and once you enter this Tritonke pole region, the structure of the expansion is naturally completely different. And now, does the original expansion know this? So we can just apply these techniques that I've described and start at x equals plus infinity. I think the data here was with 50 original terms. And you can extrapolate down to some point near zero, get very high precision values for the function its derivatives, and then re-expand in Pade, and you discover that the solution has a structure very much like this. When I say very much, I mean to something like 30-digit precision with 50 input terms. So indeed, the coefficient of the leading term is 1 to very high precision. The next few terms are 0 to 30-digit precision. The next coefficient is indeed 1/10 of the location of the first pole, meaning this value. The next coefficient really is 1/6. The next coefficient is the other constant that you didn't know in advance, and you can get 30-digit precision of this. The next value, the coefficient is 0, and this number here is indeed x pole squared over 300 to very, very high precision. Moreover, you can now look at the exact connection formulas. A lot is known about this function. It's been quantified from many different approaches. And the connection formulas, as you rotate by 2 pi over 5 or 4 pi over 5, can now be confirmed using this Pade conformal extrapolation. So that's encouraging. It's not that we needed 1,000 terms in this expansion. It's, you can get very good precision with maybe 10, 20 terms, and very, very high precision if you go to something like 50 or more. But we can do even better than this. In fact, much better than this. And that's the question, can we push this to optimality? So this is based on a paper with a video from a couple of years ago. And again, I'm not going to discuss proof, I'm going to discuss applications of this and what happens if you try to use it. So here's the general problem. You've got some Riemann surface in some variable W or omega, and it has some structure that you would like to understand. And in general, you're going to be given some number of coefficients of the expansion of your function around the origin on this Riemann surface. Now, if you knew the structure of the Riemann surface, namely you knew where the branch points were and the various structure of, say, the natural branch cuts, you could make a uniformizing map into the unit disk in general, which can be normalized like this. And then the question is, within a generic class of functions on this Riemann surface, this is the optimal thing you can do. Take your original expansion, apply the uniformizing map into the unit disk. Remember, it's normalized so that 0 maps to 0. It really is just a question of normalization. Step 2 is you re-expand your function now in Z, around Z equals 0. It's analytic inside the disk by construction, if this is the uniformizing map. The slightly subtle thing here is that you re-expand to exactly the same order that you started with. No more, no less. If you go on either side, eventually you lose precision. And then you can now use whatever technique you want to try and analytically continue within the unit disk, such as Pade or some variant of Pade. And once you've done that, you can map back using the inverse map to the original plane. Now, explicit maps are known from Riemann surfaces for certain structures. If you have three branch points or singularities, or in more complicated situations with more branch points with symmetries, things may be repeated, they may be symmetrically located around the 2 pi. We also came across and we're not aware of whether this was known in the literature before, but the explicit uniformization of the Borel plane of all of the truncated solutions of the plane of A 1 through 5 is given in terms of the inverse elliptic norm function. And I want to stress that if you go to more complicated Riemann surfaces, of course, there is this blanking on the name, this Schwarz-Christoffel construction that you can use to generate these maps. And so that can be done numerically, but it's very hard to find explicit maps beyond this uniformizing limit. However, in applications, it's very often the case that 1 or 2 or 3 dominant singularities control the main behavior of the function, and working just with those can gain dramatic improvements of precision. So let me show you how this works in practice. Let's look at the example where we have 2 collinear branch points and branch cuts, which I've normalized. You can renormalize these things so that they're equally spaced about the origin. And this is the explicit map from this W plane, which has these 2 cuts, into the unit disk here, is in terms of the modular lambda function. So Z is the coordinate inside the unit disk, and W is the coordinate on this Riemann surface here. So I'm going to switch, hopefully, just bear with me, to a Mathematica file and show you how this works. I hope I can do this. Okay, do you see that, somebody? Do you see a Mathematica file?
Yes.
Okay, great. All right, so what's going on here is, remember, this is the W plane with these 2 cuts from 1 to infinity and -1 down to -infinity. Here's a point in the W plane, and this is the unit disk that the uniformizing map maps into. But the uniformizing map maps this first sheet here inside this hyperbolic parallelogram with the blue lines here. So it doesn't map it into the whole unit disk. It maps inside here. The second sheets, depending which way you rotate, are within this hyperbolic parallelogram. And if you go another way, you end up in this Riemann sheet, or this, and so on. I could fill in the gaps here for the next sheet and the next sheet. And the point is that you can explore the entire Riemann sheet here just within the unit disk, because after the map, it's analytic within the whole disk. And as you move around here, we'll move around on the Riemann surface in the W plane. So let me just show you how this works. I'm going to move, and hopefully you see the blue dot on the right-hand side moving correspondingly. I approach the cut, which is the edge of the first sheet, and now I cross onto the next sheet, and now I have a choice. I can go this way or this way. The dashed line represents the line in between the 2 branch points here. So if I go that way, I cross back through the gap, and now I can either go this way and cross that cut onto a next sheet, or I can go this way and cross onto the next sheet here. Or from back here, instead of crossing back between the 2 branch points, I could have looped around here and crossed that cut onto another sheet. Had I started at the beginning here, instead of going that way and crossing that, I could have gone that way and crossed that, or I could have gone down here and so crossed around that way. Okay, so the point is, hopefully that gives you some idea of what's happening. If I repeat all these hyperbolic parallelograms here, I cover the entire Riemann surface over here. But if I have the structure of the function within this unit disk, I can freely just wander around on the Riemann surface without hitting any problems. So now let me go back to where I was, I hope. We can now take advantage of that to not just analytically continue and extrapolate on the first sheet, we can actually go to other Riemann sheets, even from a finite truncated expansion. So I'll come back to that in a specific example later. Now, these are cases where you know something about the singularity structure, so you have an explicit uniformizing map, maybe. But an offshoot of this is that there are also near optimal numerical methods that enable you to probe much, much more accurately near the singularities and near the branch cuts. And these are the most interesting places. So one of them is called the singularity elimination method. And it works like this. Suppose the function has some behavior near some critical point, branch point, so that as you approach that branch point, there's some index, and this is some function that is analytic at WC, and this function is also analytic at WC. So that's a fairly generic behavior of a function as you approach an isolated singularity. And what you would like to know is, where is this, what is this, and what is this, and what is this? So here's the trick. Suppose you have some idea what beta might be, either from a Padé analysis or a conformal map, rough conformal map. You can test whether that's correct by doing the following trick. You can make a linear transformation, which is a fractional derivative operation, which converts the index to a half. It's very simple. Instead of dividing by n factorial, divide by n plus something factorial, if this were a Borel function. You can just do it at the level of the original coefficients. If you did manage to convert it to the index being a half, if you then apply a subsequent conformal map, and there's a list of conformal maps that achieve this, you actually remove the singularity completely. And it's very easy to detect something that's analytic and something that's not analytic. So you can, if you didn't know beta, you can tune it until you see that the residue goes to 0 and the singularity is removed. And the point is, even if you didn't know the point of the value of WC or the value of beta, you can iteratively use a sort of resonance method to hone in on these values. And it's extremely sensitive, and you can tell very easily as you approach the location here and the index here. Once you know these, once you do this conformal map and remove the singularity, the expansion at this point just gives you the coefficient of this coefficients of this expansion. If you then want to probe this, you just now divide by this and do it the other way around. So this gives you very high precision access to the location of the singularity, the index or exponent, and also the fluctuations. It also enables access to higher sheets, which I'll come back to later. And once you've removed that singularity, you can actually then move on to the next one and the next one. And depending how much information you have to start with, you can proceed to learn a lot about the structure in the Borel plane. So let me just show you the sort of almost ridiculous precision of this type of behavior. Suppose you have just one isolated singularity. There's an exponential distortion introduced by the uniformizing map. So here's an example of a single isolated singularity, which I put at, I see I'm calling the Borel variable t now, sorry, I was calling it p before. I've located it at -1. You make this elliptic gnome function transformation, that's the uniformizing map. And now I'm plotting here the ratio of the approximate function to the exact function using 20 terms. So approximate means you start with 20 terms. And blue here is if I just do Padé on the approximate truncated guide. And you see it's actually very accurate, but as you get very, very close to the singularity, it's hopeless. The orange line here is if you do the conformal map based on the location of this isolated singularity. And you see it's much better than just Padé, but it also bombs as you get close and closer to the singularity. If you use this uniformizing map, which again is absolutely trivial to apply, no more difficult than the conformal map, you see that the precision is almost absurd. And in fact, what's going on here is this, due to this exponential distortion, if inside the Z disk, you want to get close to 1, which say is just 0.9, that means you're probing T close to the singularity at the order of 10 to the -40 precision. And this is generic, this type of behavior. Near these singularities, this is what happens with the uniformizing map. And this is part of the reason why you get such dramatic increase in precision. So if we go back to that Penleve-1 problem and now use a uniformizing map instead of the conformal map, we get much better precision inside this pole region. So I don't know if you can see it very well. There are some red dots here, but there are also some black dots. Hopefully you can sort of see that. The black dots were what came with the conformal map, and the red dots, with the red dots coming from the uniformizing map, you get much further into the pole region. And you can even do now very high precision sum rule tests. So remember that these things are approximately like a Weierstrass function, just distorted by this 5/4 power asymptotically. So since it has this pole expansion, we know that there must be relations between all of the poles and any given pole, and also this H parameter, which is the, if you like, the boundary condition coefficient at the location of one of the poles. And so there is this entire hierarchy ladder of these so-called sum rules, which are just like Eisenstein series for the Weierstrass function, which give you some self-consistency among about the locations and the strengths, the residues at these pole locations. Here, it's not a perfect lattice, it's a distorted lattice. Nevertheless, these sum rules hold. And you can check these to extremely high precision using these uniformized locations of the poles and H coefficients. All right, so, that's an example where Penleve-1 is a very well-studied, very explicit nonlinear differential equation. So we have at our fingertips many different approaches. Now I want to switch gears a little bit and talk about problems where we have much less analytic control, but which are still of interest. So for the mathematicians in the audience, this may sound a little different, but feel free to stop me if I say something too unfamiliar. In quantum field theory, there is a major outstanding problem, which is the phase diagram of quantum chromodynamics, the structure of subnuclear physics. So what's going on? As a function of temperature and essentially density, the structure of matter changes dramatically. And we know some things about this phase diagram, but we actually know very little. We live somewhere here. We can do calculations reliably sort of along here, sort of along here, up here, and maybe near here. But the places we're most interested in studying are near where we live and near where, say, in astrophysical applications. And also this proposed critical point in the phase diagram, which is the subject of a lot of experimental investigation using heavy ion collisions. And we know embarrassingly little about this phase diagram experimentally, but also theoretically. And one of the most common theoretical strategies is to make a completely uncontrolled approximation, which is to use an imaginary chemical potential rather than the real chemical potential, generate a few terms in an expansion, and simply analytically continue by changing mu squared back to minus mu squared. So, extremely primitive approach, but that's the best people can do at present. And probing near this critical point, there are very few analytic techniques we have. So one of the questions that's been motivating me is it possible that if we had some information generated in this region or this region or this region or this region, could we actually do something better about extrapolating to the region of interest? And if we want to look near the critical point, we need to be able to access higher sheets. We know something about the local behavior at the critical point using physical arguments of universality, but we don't know any of the details. So QCD, of course, is very hard, but there's a model that captures a lot of the physics of this, which is a chiral random matrix model due to Stefanov and collaborators from now quite a long time ago. And this is characterized by something called a partition function, which is a matrix integral over n by n complex matrices with some structure here which involves the mass of the quarks, the chemical potential, and the temperature. And this partition function at finite n has certain zeros which have physical meaning and are called Li-Yang zeros by physicists. And this is the phase diagram and the temperature, chemical potential, and quark mass plane of this chiral random matrix model. And it approximates quite well the expected behavior of this part of the QCD phase diagram. That's why it's of such interest. Okay, so that's the physics background. Now we can make things a little more precise mathematically. Here's a partition function in terms of n by n random matrices, so you're integrating over these n by n complex matrices. In principle, we've been interested in the large n limit, and the pressure is basically the log of this partition function normalized by 1 over n. And from that pressure, we can calculate certain things that can tell us something about this phase diagram as a function of temperature and chemical potential. And it'll be done at fixed values of m, so you can think of just slices of this phase diagram at fixed n.
I have a brief question.
Yep, sure.
Is phi ranging over all possible n by n matrices?
All complex n by n matrices, yes.
Okay, thank you.
So the things that experimentalists are interested in and the physicists, theorists would like to be able to calculate are things called susceptibilities, which are basically derivatives of this pressure. And the thing that is usually calculated using existing techniques and fitted to experimental data are these small chemical potential expansions of these. So they're coefficients that are functions of temperature and implicitly also functions of a fixed quark mass. But these are expansions generated somewhere here. But we're most interested in the behavior around this point or this point here. So we can mimic the situation in QCD, but just by taking this random matrix model, where it's now much easier, of course, in QCD of calculating these expansions because it's much more explicit. But we can look at what happens with finite order mu-squared expansions of these so-called susceptibilities. So we can apply these Pade tricks with conformal maps, without conformal maps, and see what happens. So first of all, if we apply Pade with, say, n equals 12 or 20 or some number of that order, we discover that there's a complex conjugate pair of dominant singularities, which if we then use the conformal map trick, will absolutely nail their location because it's much more accurate. Pade puts fake poles along this line here because of what Pade is trying to do is to represent a cut along here and a cut between these two by placing poles there that are doing nothing but trying to represent a cut. Whereas the conformal map is very accurate near the cut and just nails these locations of the Li-Yang singularities. And since they're square root type singularities, that's all that's left of the conformal map. So it's much, much more accurate near what would have been a cut, but also near the singularities. So now we can use those analytically continued either with conformal map or without Pade approximations and compare with an exact answer, because we can actually calculate exact answers with this random matrix model. So here's the second susceptibility, just called the susceptibility. And the exact answer, I hope you can see, is this dashed line here. And if you just use the Taylor expansion, so let's say 20 terms of the Taylor expansion, this is the magnitude of the Li-Yang 0. So this sets the radius of convergence. So that thing goes haywire when you just go along the real axis, but you're controlled by a complex, the location of a complex singularity. So that thing can't be pushed anywhere beyond the magnitude of the Li-Yang chemical potential. If you use Pade, you can go a little further and you see the turnover of this. But if you apply the conformal map, you can go much further and map out the structure of this bump here. And I stress that we're using exactly the same input data. It's just processed differently. And they're not they're not more difficult. It's just one more simple step. If you apply it to chi4, which is called the kurtosis, which is a physically relevant susceptibility, then again, we see the exact is this dashed line. The truncated expansion is completely hopeless at describing this turnover and this turnover. And the Pade approximation does reasonably well at getting this turnover, but cannot access this behavior here. Whereas with the conformal map, which is the blue line, we see that it's structurally quite close. And this would be, extremely accurate in the level of the precision of experiments. So that's encouraging. But we can actually do something more. If we're interested in probing near this would-be critical point, then there are, we can invoke what are called universality arguments in physics, which are basically scaling relations looking very close to the critical point, which argues that the structure of what's called the effective potential, which governs the behavior of very close to the critical point, can be described by this fourth order polynomial with two parameter coefficients. And as these coefficients vary and even change signs, this effective potential has a structure maybe of a double well, or maybe of a tilted double well, or maybe it can have a structure where there is no double well. And that reflects the different phases of the system as you vary these two parameters. And near the critical point, this generic fourth order polynomial has a nice scaling relation. And so in what's called a mean field approximation, this can be rescaled so that the minimizing of the effective potential just becomes this simple cubic equation. So if all that sounds like gobbledygook to you, don't worry about it. I can state the problem as, let's try to uniformize this cubic just from a finite number of terms of the expansion on the first sheet of z as a function of w. Okay? And if one could do that, one could accurately analyze the vicinity of this critical point within this mean field approximation and even beyond. So this is a cubic. I've just normalized it to clear away all the not relevant parameters. And there are obviously three sheets. The first one, what we would call the natural first sheet, which has two cuts, say from, it's not, I can normalize them to be 1 and -1, but here I don't think I normalize them to be that. We'll refer to as the high temperature sheet, because that's the region in which these parameters are such that it corresponds to the phases at high temperature. The next sheet, I'll call Z2, one of the other solutions of this cubic, is what's called the low temperature sheet. It just has one cut. This is some Mathematica artifact, so don't worry about that. It just has one cut. And there's a third sheet, but it's related to the second sheet by this obvious symmetry. So we really need to think about two sheets. And physically, they correspond to the behavior at high temperature or at lower temperature as a function of mu. So the behavior at high temperature or low temperature, depending where you are on mu, is quite different. So since this is solving a cubic, we know exactly how to uniformize this. And so if we start with the high temperature expansion of the, say, first sheet solution of this cubic, here's an expansion around omega equals 0. It's uniformized by this modular lambda function. And here I have a picture of the high temperature sheet in the W plane. So there are two cuts from, say, -i down to -i infinity and +i up to +i infinity. You have to do a little bit of rescaling to get rid of some √2 factors, but that's not important. And what we're going to do is use this uniformizing map to map to the tau plane. So that's probably what people are more familiar with in mathematical literature from this modular lambda function. So it maps this sheet into this region in the modular plane. But then we can make a further map into the unit disk by this, it has a special name. I've forgotten what the, Cayley transformation or something, which maps into this hyperbolic quadrilateral here. And the color coding is such that this gold maps to gold, blue maps to blue, etc. And the boundary between the upper and lower parts of the complex W plane correspond to this circle here, or half circle here, and correspond to this line in the zeta plane. So now we can try, imagine we're in a situation where we only had this original mu expansion to some finite order that translates into this equation of state to some finite number of terms in this W expansion for Z, but that's an expansion generated on this first sheet, where we expand around W equals 0 on the first sheet. So the first thing we would like to do would be to extrapolate to other places on that first sheet. And that corresponds to doing this and staying within this hyperbolic quadrilateral. And so if we just take 10 terms of this expansion in W and make this uniformizing map, we can now try to extrapolate along this real axis of W. And the exact answer is this Z1 function. And it's this shaded curve here. I hope you can see it under the dash. There's sort of a gray-blue line here. By comparison, if you just took your truncated expansion at 10 terms of this expansion and tried to go away from W equals 0, you would die because of these singularities here, even though you're going along the real axis. And that's these vertical lines here with these dotted lines. The Taylor series is just hopeless, even after 20 terms, using 20 terms. If you applied Pade to this expansion around 0, you would get this red dashed curve. And so you see it's much better in the vicinity of M equals 0, and it goes beyond, it's accurate beyond the distance of these locations of these leading Liang singularities. But if you do the uniformizing map, and actually the uniformizing map here was just with 10 terms, and the others are with 20 terms, that's the black dashed curve. So you see, it's almost a joke. It's so much more precise going along this physically relevant on the high temperature regime, extrapolation to higher, to further away from the original expansion. So that's encouraging, and this is based on a very small number of initial terms, and the uniformizing map just pushes the extrapolations much more accurately. But we can also cross onto the low temperature sheet. So this corresponds to doing exactly what I was showing on that when I was showing you that Mathematica file. We're going around, say starting here, going around and jumping onto the next sheet, coming out on the next sheet, and going around on here and trying to probe this next sheet. And this is a low temperature sheet. It has a very different structure compared to the high temperature sheet. And that's what we want to try and reproduce. So here in the W plane, the low temperature sheet has just one cut. So I've normalized here to go from I to I times infinity. This is just the image of where that other branch point would be. And this, under that same uniformizing map, this guy ends up not here, that was the image of the high temperature plane. It ends up in one of these, inside one of these semicircles down here. And if you then further map into the unit disk, this is with exactly the same transformation, then you end up in one of these corners. And so this is another hyperbolic quadrilateral, which is the representation of the second sheet under a particular transition across cuts. So if you remember what I was describing before in the animation, if I start at the origin on the high temperature sheet, which is this, let's call it the first sheet, and I move, say this is the omega plane, and I move across to one of the cuts and jump onto the low temperature sheet and try to then keep continuing on the low temperature sheet. This is that trajectory. I start at the origin of the unit disk. I'm on the high temperature sheet. I do my mapping, re-expanding, my Pade, whatever I want to do to analytically continue within the unit disk. And I just freely wander in the unit disk. And I just go like this. I cross here, nothing dramatic happens. I just automatically pass onto the next sheet. And then if I go this way, I cross this again and go this way. Had I decided in the unit disk to go this way, I would have just rotated the other way and crossed onto the low temperature sheet in a different direction. Okay? And the point here is, all I need to do to implement this, to cross sheets, it's absolutely trivial. I just take my original expansion, map it with this uniformizing map, I'm now within this unit disk, and I can, once I do a pade or something, I can wander through this. And if I want to know where I am on the original W plane Riemann surface, I can just refer to what this point is doing. So once I go onto the low temperature sheet, that's physically, there are only two sheets that I'm interested in here. I can now do my pade or something inside that unit disk. And now I can follow the behavior on the low temperature sheet. And here's a plot of what this imaginary part of Z versus the imaginary part of W, that's the relevant physical function. And the exact function is this shaded stuff here. It has this interesting switchback structure going through these special singularities. And so this is jumping from Z1 to Z2 to Z3, crossing the sheets perfectly. And the uniformizing map is the dashed line, and you see it captures all of this beautifully. And here's a zoom in of the behavior very close to this. And if you tried to do this without the uniformizing map, even with a conformal map, you simply can't do this because you're not taking enough information with you when you do the map and re-expansion. So this was a sort of proof of principle that with some not unreasonable number of terms, here 20 is maybe too large, but even with 10 terms, you get very accurate up to about here or somewhere. It's at least feasible to be able to go onto another sheet, and you don't need to know the whole solution to the problem. Here we're just using this basic quartic behavior, which is the characteristic of the very close vicinity of a critical point within a large class of problems. And of course, if we wanted to go even further, or if there was some other critical point nearby, it would be a much more complicated problem. But this is what I said, that very often in physics, we have isolated singularities, which we want to probe very closely. And under those circumstances, there's actually a lot you can do using fairly simple conformal maps and uniformizing maps. So I still have a few more minutes, I think. So I want to show you one more example, which is another example from quantum field theory. And this has a long storied history. Here I'm showing for your amusement the abstract of this famous paper by Werner Heisenberg. And the Euler you're thinking of is not the right Euler. Hans Euler was a student of Heisenberg. This is a paper published in the mid-1930s, long before what we really view as the birth of quantum field theory. And yet they did a fully non-perturbative quantum field theory calculation, including charge renormalization, already back in the mid-1930s. It's an absolutely spectacular paper. It's also quite impressive that they managed to convince the editors to put such a complicated looking equation in the abstract. But this is the paradigm of what nowadays is called effective field theory, where you integrate out the degrees of freedom above a certain mass scale, here the mass of the electrons, and just keep the low energy degrees of freedom of the light degrees of freedom, which here is the photon. So this is quantum electrodynamics integrated out at the fermion, at the electron mass scale, done in a constant electromagnetic background field. So here E and B are the strength of the electric and magnetic fields. Technically, the problem is this. Calculate the log of the determinant of this Dirac operator. So the Dirac operator, there's a slash, means contracted with the Dirac matrices, so first derivative. And this is a gauge field, a mu, which characterizes this constant field strength electromagnetic field. In general, we want to do it not for constant field strengths, for very inhomogeneous fields, but this was the original calculation by Heisenberg, where they did it for a constant field strength. And they're able to get this exact Borel representation of this, what's called a one-loop effective action. An absolutely heroic calculation. So the open questions are, this was what's called a one-loop calculation. Can we do this at higher perturbative order in the fine structure constant? And the more relevant question physically is, can we do it for not constant electric and magnetic fields, but inhomogeneous fields. And actually the relevant question is in extremely inhomogeneous fields. So this is what I mentioned at the beginning of the talk, that the behavior of QED under extremely intense fields is completely unstudied, both experimentally and theoretically. The general formalism was established by, this reads like a Nobel laureate playground here. Heisenberg, then Salam, Schwinger, Feynman, Nambu all worked on the formulation of this problem. And there's a general representation in terms of Fredel determinants, but unfortunately it's quite difficult to implement in the very inhomogeneous limit. There's a beautiful word line representation due to Feynman and refinements from Nambu. And there's, of course, the WKB approximation, which was pioneered by Keldysh in atomic physics. And this was actually Edward Brezan's PhD thesis to apply this to the full QED situation, and also work by Popov and Marinoff independently. So the loop expansion of this effective action would be an expansion in the fine structure constant with coefficients that are themselves asymptotic expansion in the field strengths. So this formula on the previous page, this is L1. But of course there's L2, L3, L4. There are various conjectures about the high orders. There's a famous conjecture that the imaginary part of this, when there's an electric field, so there's pair production, in the weak field and all orders in the fine structure constant is conjectured to exponentiate. We only have actual information at one loop and two loop, but there are arguments about this, but it's by no means settled, and three loop has been an absolute roadblock that people haven't been able to penetrate beyond. There's also a conjecture due to Ritus, who pioneered a lot of these strong field calculations, is that actually the effective expansion parameter changes if you're in the background of a constant cross field. So these are constant electric and magnetic fields that are perpendicular, which is it's an approximation to a plane wave field. But the actual expansion parameter changes from just alpha to alpha, this parameter chi to the 2/3. Also, almost nothing is known beyond two loop, but there are conjectures. So these are the sorts of things that motivated me to look at some of these extrapolation methods. So let me just show you a couple of examples. So here's that one loop expression of Heisenberg and Euler, just for the case of a magnetic field. So we see the Borel transform function here as a nice meromorphic function, just with isolated poles along the imaginary axis. Here's the weak field expansion, simple to generate. There are factorially growing coefficients. There are zeta parts to the coefficients, which asymptotically, of course, 1, but these just represent the higher exponential corrections due to the higher order poles in this meromorphic function. So this is a simple standard alternating sign factorially divergent series of the class that I described right at the beginning of the talk. The strong field expansion is known by general arguments due to Weisskopf and Heisenberg, which nowadays is the renormalization group interpretation. And this factor 1/3 here is the one loop beta function in QED in this normalization. It's just the coefficient of the b squared log b behavior. So now we can ask the question, suppose we didn't know this, and we didn't know this full expression, and we didn't know this, but we just knew some number of terms of the weak magnetic field expansion, let's say 10 terms. Can you extrapolate from weak magnetic field to strong magnetic field? And can you rotate from B to IE, which is the analytic continuation that turns a magnetic field into an electric field? And the answer is surprisingly yes. Here over, I think, 6 or 7 orders of magnitude. So the light blue thick curve is the exact answer from the integral representation, which we happen to know. The orange curve is 10 terms of the weak field expansion. So of course that behaves like a typical asymptotic series. And the red curve is this leading strong field behavior. And you see the extrapolation, even with just 10 terms, goes beautifully between this. And since this is meromorphic, all we need here is paired data. And now for the exponentially suppressed imaginary part, this is exponentially suppressed in the weak field limit. The blue dots are the extrapolated values, and red is the exact value. And you can just see gold here, which is the WKB expansion. And now you can see you can extrapolate over many orders of magnitude. There are also subleading exponentially suppressed terms that are accessible. The same thing can be done at 2-loop, where there is no such Borel representation, but you can generate some terms of this. And it also works similarly accurately. If I may have just 2 more minutes, let me just mention what happens when you go to an inhomogeneous field. This is really the burning question in this field. There's a couple of soluble cases where the magnetic field has just a one bump type structure, or the electric field has just a one bump type structure, which can be solved. You can look up the solutions in Morse and Feshbach. They're standard solutions. They're just hypergeometric equations in disguise for the Dirac operator. You can also reduce it to a single Borel integral using some tricks. And then you can study analytic continuations from the B field to the electric field, from the spatial inhomogeneity to time-dependent inhomogeneity. There's a governing inhomogeneity parameter established by Keldysh, which is basically the scale of the inhomogeneity in the basic unit set by the strength of the field. So it's something like 1/b lambda or omega over E in units of the mass and the charge. There's also the WKB approximation, which changes this exponent by this factor, which is an explicit function of this inhomogeneity parameter. So as gamma changes, you change from a slowly varying to a rapidly varying field. So the question is, can you do this just starting from an expansion at weak field with coefficients that now depend explicitly on this inhomogeneity parameter? And already from the behavior of these coefficients, you learn that there's not just one leading branch point, which is what the WKB approximation suggests. There are actually 3. And these 2 are subleading, but they become important when gamma becomes larger. So when the field becomes more and more inhomogeneous. So I'm not going to go into the details of this, running out of time. Let me just say that you can actually see these in the conformally mapped plane. You can distinguish, as the inhomogeneity parameter varies, you can distinguish which one becomes more dominant than a repetition of a previous one. If anyone's interested in that, I can explain it more later. Let me just show you the resurgence structure. The large order behavior of the coefficients has some factorial behavior, some leading location of the leading singularity, some prefactor, part of the Stokes constant, and some subleading large order corrections. And now if you look at the fluctuations around this leading world line instant time, this is that WKB expression that I showed you before. There are corrections to it that match exactly what you would expect from the large order growth of the perturbative coefficients. You can also do this for the other Borel, looking near the other Borel singularities and for multi-instant times, but it's exactly the same thing, but the formulas just get a little bit longer. So once we know that, we can be more hopeful that we can apply these analytic continuation techniques. And let me just say quickly that the same structure applies. Even in this problem, if I fix gamma to be small or large, with just 10, 15 perturbative input terms, we get perfect extrapolation from the weak field expansions to the strong field expansions, even at very inhomogeneous fields. And in the electric field case, looking at the imaginary part of the effective action, this exponentially suppressed term, we see that the red line, which is the extrapolation here, follows the exact answer very accurately. And the brown curve here, the orange curve, is the WKB approximation, which fails quite badly for very inhomogeneous fields. So sorry, that was a bit rushed. Let me just now go to the conclusions. The main point of the talk, I hope I've convinced you that there's some hope that these novel extrapolation techniques, which are actually not that complicated, give some hope that we can actually go from some weak field or perturbative regime or adiabatic regime into the strong field or non-perturbative or non-adiabatic regime, using some fairly systematic steps for which we can understand the level of precision of each step, not just doing some random thing for this problem and another random thing for another problem. The tools are very simple. They're just conformal maps and uniformizing maps. And even if you just apply them to the leading singularities, you get dramatic improvements over doing nothing. I showed you 3 examples, this Penave going from the original asymptotic expansion at large X on the positive line into the pole region. Showed you this chiral matrix model where you could go from the first sheet to the second sheet just directly using this uniformizing map. And there's Heisenberg-Euler case where you can see strong evidence for this parametric resurgence, and you get much more precise analytic continuations. There are many open questions in the field theory applications, higher loops, resummations, more general inhomogeneities, the effect of noise as a subject of a recent paper, and there are many, many other potential applications. So let me stop there. Thank you.
Thank you very much, Gerald. So it's time for questions and comments.
Maybe I can ask a question, and this may reveal the hole that there was between the train and then I came home. But nevertheless, does any of this come with some kind of error estimates so that you can see that when you apply these conformal transformations, how much you actually gain over the Taylor series and then over the Pertubation when you add the conformal?
So for example, so if you stick to a particular map, which will uniformizing a particular Riemann surface. So now you have to stick to the situation where you have just 1 or 2 or 3 singularities, then the maps are completely explicit. You can do error estimates. Let me just give you the example. The simplest example would be to go, see if I can, so remember the example right at the very beginning when you were still on the train. You had just this leading singularity with a factorial growth, right? So there's this explicit conformal map in terms of Jacobi ratios of Jacobi polynomials. Then there are absolutely explicit error estimates both in the Borel plane and the original plane, and that's where this 1/n squared over n to the 4th scaling. That's just a leading scaling. We have explicit expressions for the error estimates. So these things, I think, are only possible when you have explicit representations of the maps, because we use that in order to get what the related special functions are, and then you have to use asymptotics of those special functions. That might not quite be true because the basic Szego structure relates these Pertubation tricks and these conformal maps. They're intertwined in a way that maybe you could generate approximate error estimates from there's a basic functional that's being minimized by this Pertubation, that's the result of Szego, which is related to orthogonal polynomials, possibly not on some real interval, possibly on some complex interval. And it's that functional which tells you ultimately what the precision is. So in certain cases, that function is explicit enough that I can write nice formulas. But I don't know, maybe Vidya can correct me, but I suspect it may be possible that knowing something even numerically about that functional might be able to translate into error estimates. So
yeah, I mean, in general, I mean, what we showed is that error estimates are in terms of the uniformizing map. I mean, close to the origin, the gain in accuracy as a factor is related to the capacity of the Riemann surface, something that you can quantify and probably approximate numerically.
So if the maps are explicit, then there are expressions for the capacity. But if maps not explicit, then there's an interval expression for the capacity, and maybe you can evaluate it. But
estimate that in some way, right?
The point is, in physics, it's very common that there's a dominant isolated singularity. And in that case, you can be completely explicit. And that's what we did in that short paper a few years ago.
But I was also interested in sort of the relative speed up of accuracy between the different methods that you showed. Can you say something about that?
Yeah, so for example, again, let me go back to, I think it's easier if I can show you some formulas to go with things. So this is a comparison of let me give you a comparison of 3 things. Oops. So suppose you had some truncated expansion like of this expansion, right? So factorial growth, possibly with some offset. Okay, so a generic situation. And you were actually interested in the function back in the original X plane. So it's sort of an integral of this, Laplace transform of this. So the first thing you could do is you could take the original expansion in X and do pade with that. Oh no, actually, the first thing you could do is just truncate. And of course, we all know that's hopeless, right? You fix the truncation order and then you try to decrease X, of course, it just goes haywire, okay? So as a function of n, that gets worse as you increase n, the relative precision. Okay, so let's forget about that. The next thing you might think of doing is doing pade in the X plane. Okay, so now you can do that. And again, there's some known polynomials. You can analyze their large order behavior. And then in that case, the precision scales like 1 over n, where n is the number of terms. And so that just comes from asymptotics of some other functions. Okay? But now if you first go to the Borel plane and then do pade, you gain 1 factor of n more. It scales like 1 over n squared. So we know all the coefficients and offsets and subleading corrections. I'm just giving you the leading. Okay, and that's completely encapsulated in the asymptotics of these Jacobi polynomials, which is totally understood. Now you can do the case, again, same input data, but before you do pade, you do a conformal map and re-expansion, and then pade. And now it scales like n to the 4th. And again, all the subleading corrections are known and whatever. They just correspond to Jacobi polynomials again, but with different arguments and different indices. So it's 2 alpha instead of alpha. So there's a 2 alpha here. You gain an extra factor. And so in that situation, can be totally explicit. I could repeat the same type of discussion with the uniformizing map, but I don't have it at my fingertips. And that's, I was just resorting to these types of pictures to show it's really dramatic.
But the uniforming map, would that give you something stronger than n to the 4?
Definitely.
Yeah. Would it be exponentially better than that?
I suspect so. Yeah, in this case, I can do that calculation, but I haven't done it because this is also completely explicit. This is just the elliptic norm function. So we know everything about this guy too. And I think it would come from this exponential distortion that's happening here.
Right.
Yeah, actually,
yeah, super interesting. Excellent talk. I wish I'd seen the whole thing, but I couldn't. Yeah, impressive.
By the way, you might be interested. We've been applying this to some Chern-Simons theories. There'll be a paper coming maybe sometime in the next decade or so.
Which manifolds is this?
Oh, various surgeries on hyperbolic, not manifolds. The point is you can go very, very far in the Borel plane. There are very, very distant singularities, and you can just nail them with these techniques. And if you don't use these techniques, it's just completely invisible.
And please, may I ask questions?
Sure.
May I ask questions?
Yeah, sure.
Yeah, I have 2 questions. At first, thank you very much for a very interesting talk. First question is follows. There are design theory and the theory of association schemes that applies in approximation theory. And for instance, in design theory, there is a very small, very simple example how to approximate a finite set. This is the example of projective plane on 7 points. Do you have similar or do you know some simple examples that demonstrate your approach? This is first my question. And second question, in some sense, opposite. What is the general framework of your considerations? It is right that this is the action of groups on homogeneous spaces, as, for instance, Jacobi functions appear as functions under the action of groups on homogeneous spaces. So these two questions. Thank you.
Okay, thanks. So I can't say very much about the first question because I'm not familiar with this design theory, but the case where we can really quantify things are the cases where you know the explicit uniformizing maps. So the explicit uniformizing maps is known with these three punctures. So in those cases, we can be absolutely completely explicit. And I should do the calculation that Jürgen suggested. So that would be sort of the prototype for this setup. And the reason it's interesting in physics is that very often the problem, or a very complicated problem, is governed by 1, 2, or 3 dominant singularities, and that then can be covered. And the examples I showed you were cases where I didn't do a complete uniformization. I just did uniformizations based on leading singularities. And I hope I demonstrated that even this approximation leads to quite dramatic improvement over simpler methods. So I'm very curious to learn about this projective plane example. So if you could maybe send me an email with some references. I'm just not familiar with it. I'm not, it's not my field. The second question was, remind me. I'm forgetting what your second question was, sorry.
Second question, what is the general framework for your theory?
Yeah, so the general framework, the general optimality theorem is, if you want to approximate a truncated expansion of some function on a particular Riemann surface, the best thing to do is to use the uniformizing map of that Riemann surface, which requires knowing the locations of the singularities, and truncating after re-expansion at the same order. That's the theorem. Now, you could argue, well, that's only useful in cases where you know the uniformizing map, but the point is that's actually not the case. Applying this procedure, even in cases where you only know a partial or approximate uniformization, does give dramatic improvements. And there are enough cases of interest in physics where we know these explicit maps for the leading singularities that it can be useful. So it's different from approximation theory, by the way. We've been referring to this as inverse approximation theory. This is not a case where we take a given function and approximate it in terms of some chosen set of functions. This is a case where we're just given some partial information about the function, and we want to reconstruct, analytically continue it, and try and learn about its global structure as best we can. So it's a little bit like the inverse scattering problem in physics, that you're given some information about the scattering data, and you want to work out what produced that scattering. We're given some data here about some perturbative expansion, and we want to find within some generic class of functions what function could have given that perturbative data. And we want to refine that and refine that and refine that as much as we can based on some admittedly practically limited amount of information. Does that make sense?
Okay.
I have questions, so maybe.
Yeah,
Are there
sure.
any other questions?
Maybe I can.
Like two kind of very concrete questions. So you were mentioning that with this method you can really explore very far the Borel plane, right?
Yeah.
So the idea is then that you take a truncated perturbative series, use the uniformizing map once you know the leading singularities, and from the Padé-Borel and from the Padé approximant after uniformization, you can read further singularities.
That's part of the story. I'd say there are two classes of problems in physics. There might be classes where you have some non-perturbative reason to think you know where the leading singularity is.
Yes.
You might think it's due to a Renormland or an instanton or some saddle thing. So you might have a guess, right?
Yes.
And you'd like to confirm that guess. And the point is you can bootstrap this idea to test whether that guess is correct. For example, the singularity elimination. Suppose you tell me some critical point has an index, 5/16, right? Some Ising type system. Okay. I can take those coefficients, I can multiply them by some appropriate gamma functions, turn that into a 1/2 singularity. Okay. But that was based on guessing that I was at 5/16. Now I do my conformal map and that should disappear. If I didn't get 5/16 right, it doesn't disappear. You're left with a line of,
yes.
And the point, it's surprisingly sensitive to that. So you can iterate both the location and the index. If you didn't have the location right, it would also fail, and it would fail spectacularly. It's not, a question of not quite working. It's really easy to tell the difference between getting it right and not getting it right.
Right, but in some cases, for example, you really know where are the singularities, right?
Yeah. So then that's
the leading singularities for sure, right? Okay. And then what you're telling me is that with using this uniformization map, I could see higher in the Borel plane than with the standard technique, right?
Yeah, definitely.
And I guess this applies also.
Also, you can go closer to the singularities, so you can get much more precise Stokes constants.
Absolutely.
And you can test connection formulas to higher. So,
right. And I guess the same applies to Borel resummation. So, with the conformal map, you have some improvement in the Laplace type of integrals. Yeah. And what you're saying is that with this uniformization map, you really get much more precision in the Laplace integrals, right?
Right.
So the message is that, in a sense, instead of doing conformal map, we should do uniformization map, right?
In situations where you know it. I showed you some examples where even doing the conformal map gives you sufficient precision and you're happy.
Right. But there are many others in which, you really would like to have more precision than conformal. So I guess trying uniformization map could improve the situation, right?
Right. And also another point here, which is clear to physicists, is that a lot of the discussions of resurgence in the mathematics literature considers generic locations of singularities. But in physics, it's very common that we have a leading guy, but then it's a nonlinear problem, so it's repeated it twice, 3 times. So you get these collinear lines of singularities. And so those subleading ones are hard to probe because Padé does something stupid. It puts a cut which covers those. So using these maps can reveal those. That's the first step. But if you use this singularity elimination, you can just remove the first one. And now you can move to the second one. You can remove the second one, move to the third one. In principle, if you had enough data, you could just keep going. And, seeing where the second or the third one is interesting in some cases. So basically, you can choose, if you suspect that there's a singularity somewhere, you can choose to zoom in on that location. And I'm not a programmer, but I suspect this could be programmed to be really efficient. But doing dumb things about approaching step by step, you can actually really zoom in quite precisely, and in certain circumstances that can be useful.
I think we have a question from Nick.
Yes, hello. First of all, thank you so much for the talk. On the what we were just discussing, to continue the train of thought, if we have kind of a lattice, one-dimensional lattice of singularities along
Yeah.
some direction, and you study the first one. What I was thinking is it possible to extract the resurgence relations from a finite number of probes, I guess, if you will?
Yeah.
Or is that something that you because,
Yeah.
right, like
So, yeah,
kind of the
so-
flavor of resurgence theory, you just need to know the structure of one to know them all, right?
Right, so this is how you would do it. Suppose you had some leading guy. So now we're in the Borel plane here, right? So what you're interested in is the fluctuations around that point. And if there's some resurgence structure there, those fluctuations around that leading singularity should be related in some characteristic way to the original perturbative guys, right? So you should be able to nail that. Now you can get rid of this guy and move to the next one. And you can do exactly the same thing to the next one. Again, in principle, with enough information, you can then extract the fluctuations around the second one of these non-perturbative singularities, right? And you can see, is it independent or is it just the repetition of the first guy, right? And, again, the number of terms in a fluctuation you can extract depends on how much information you have at the beginning. You can't do everything. No free lunch theorem kills you at some point, but that's the procedure. And in certain cases where you can generate many terms, you can see this quite explicitly. And even in the conformal map case in Penleve 1, this paper with the video some years ago, we weren't even using uniformizing maps. You can see some of this resurgent structure beyond the first to the second singularity. So the answer is, in principle, yes, but you need enough information to make it actually work.
Thank you very much.
I have a question.
Yep.
So you said that you need as many terms after the mapping as the original number of terms available. But in practice, very often happens that the first few terms are quite precisely known, and as you go higher and higher in the expansion, the terms are less and less precise. So
Yes.
can you take into account this effect?
Yes, so that's what this paper is about. So this is actually one of the most important questions in this whole field to apply to physics, right? Because in really hard problems, we're not going to know these coefficients exactly in closed form. In problems that are very explicit, like nonlinear differential equations, we have a chance of extracting them as rational numbers or numbers that we can get to infinite precision. But in practice, that's not possible. And it turns out there's a very interesting interaction between the amount of imprecision or noise and the number of terms you can use before this all falls to pieces. So that's what this paper is about. And if I can just show you. Okay, I can't see this for some reason. Okay, here we are. So here's something along those lines. Suppose you have a finite expansion, and then you add noise to them. So you add some number of noise. And you discover that if here's the fractional error in the original, so the relative error, and as a function of n, depending on the magnitude of the noise, it breaks down at some point. It just all falls apart. What that means is, if you try to use Pade to that order in n, you'll just get random distributions of poles that have nothing to do with the actual function you're talking about. And there's a universal scaling, which is that this breakdown point, so the different colors here are different realizations of the noise. And there's a kink-like transition at a certain point that depends on the magnitude of this noise. So that's not the full answer to your question, but it's a partial answer that indicates that this really needs to be studied in more generality. What's the interaction of lack of precision with all of these operations, because you can just see automatically that if you start taking combinations of coefficients, you have finite precision, you're going to lose out at some point. And that this paper is a first step in that direction. So it's not a very satisfactory answer, but I agree with you completely that this is something that needs to be sorted out more precisely.
Okay. Are there other questions? So if not, let's thank Gerald again for this very enlightening talk.
Okay, thank you.
And well, I hope I will see you at least in Switzerland in January.
Yeah. Is the glacier still going to be there?
Well, you know, there is going to be snow, probably, you know. Something there will be. Okay. Okay. Well, bye, everybody.
Yeah.